Welcome to another podcast. This episode we're going to be taking a look at the topic of antiderivatives. And we're going to approach this topic simply as the reversal of what you would normally do if you were taking a derivative. We're going to undo that to be able to take the antiderivative. So to start with, I just want us to consider, let's say a function, and we'll just pick a power function or a polynomial here since we've become very used to working with those. So here we have a cubic. And we know pretty well by now that we would use the power rule to take the derivative of this cubic function. So it would be 3x squared plus 4x minus a half. And so if I'm going in this direction, then I'm performing what we call differentiation. The question that I have, and the question that this video addresses, is what if I start with the bottom as my function, and I want to come up with a function in reverse, in other words, anti-differentiation. In other words, I want to recover the function x cubed plus 2x squared minus 1 half x plus 3. I want to come up with an operation that will reverse this and get me back to the function that I had. Well, we can sort of think through this based on just reversing what we did previously. So I think of it this way. In order to go from x cubed to 3x squared, I had to multiply by 3, and I had to subtract 1 from the power. So to reverse that, if I multiplied by 3 previously, then I should take this function and divide by 3. And then rather than subtracting 1 from the power, I should add 1 to the power. So same thing here. I multiplied by 2 to go from here to here. So to go from there to there, I multiplied by 2 and I subtracted 1 from the power. So I'm going to divide by 2 and I'm going to add 1 to the power. All right, if we keep going in this general direction, then the question is, what do we do about the 1 half? Well, I treat 1 half as if it's 1 half times x to the 0, because x to the 0 is 1. And so here what I did was, if you think of this being the power 1 on this side, I multiplied by 1, so I divide by 1. Nothing changes there. And so basically I'm just going to take and add 1 to the power, because the only thing I did was subtracting 1 from the power to go from here to here. And so if I clean this up a little bit, then this function, which I'm going to call capital F for now, and you'll see why here in a little bit, 3's cancel, leaves me x cubed. 4 over 2 is 2x to the second power, and then it's minus 1 half x to the first power. So this looks really good. It matches up term for term with all of them, except for the 3. The 3 appears to be left out of this sort of reversal. So like I said, this antiderivative is reversing this process. And so the question is, how do I get the 3 into the picture? And unfortunately, the answer is you can't, at least not without a little bit more information. Look at it this way. If I consider the function f of x actually has a constant term, let's say plus 0, then what does 0 map back to? In other words, what is the antiderivative of 0? Well, if we think about this for a second, we know that the derivative of any constant is 0. So does that imply that the antiderivative of 0, whatever that's going to be, which, by the way, we need a notation for this, the antiderivative of 0. That notation is something called the integral sign. We'll talk more about that in future videos. But what is the antiderivative of 0? So this is the antiderivative of 0. And this symbol here is called the integral. Is the antiderivative of 0 then equal to c, the original constant? And the answer is no, you don't actually get back the original constant, because there could have been any constant here. So I could have had the derivative of 5 is 0, the derivative of 4 is 0. So when you try to reverse this process, this could be any constant. It doesn't necessarily have to be the one you started with. So I might call this a C1 and we end up with a C2 here. We end up with a completely different constant. So the best I can say here is that the antiderivative is going to involve an arbitrary constant. So this is called the constant of integration, because the process of anti-differentiation is called integration. We'll talk more about that, like I said, in a future video. But this process is almost perfect. I can undo everything the derivative did, except I lose information about the constant that created this zero for the function. And so the best I can do when I go backwards is to say that there's some arbitrary constant here that was made zero upon differentiating, but I don't know exactly which one it is. So let's talk about the definition of antiderivative for a second. So the definition of antiderivative, if this example hasn't made it clear, is that the function f of x plus c is an antiderivative of the function f of x on an interval I if basic relationship here is when I do the derivative of this function f that's my antiderivative, I'm going to get back little f. So if the derivative of my antiderivative is equal to the original function f for every x in the interval. Now we write, so we have some notation for this, we write the integral of f of x dx to be equal to f of x plus c. So this integral here, talking about some of the notation here, this integral here, this is called an indefinite integral. And f of x plus c is called a general antiderivative. It's called a general antiderivative because we don't know the value of c. If we had a specific value of c in mind, so for example, if I write, thinking about the example above, if I write x cubed plus 2x squared minus 1/2 x plus c, this is a general antiderivative. But if I specify the following, so x squared minus 1/2 x plus 3, so if I'm looking for this one, then this is a specific antiderivative. And specific antiderivatives are solutions to things that are called differential equations. And so I want to close out this video by looking at kind of what the setup is for a differential equation and show how this antiderivative is the way that we go about solving differential equations. So the example here is, suppose I take the derivative of a function f of x, and the result of that is 3x squared plus 4x minus 1/2. Then my goal is to find f of x if I know that the value of f of 0 is 3. Then the answer to that is this specific antiderivative. So this is called a, together with this condition, this is called an initial condition. So this equation right here is called a differential equation because it relates a function to its derivative. We don't know what the actual function is, we only know what its derivative is, and we're trying to figure out what function it came from. And then together with the initial condition, This is something called an IVP, or initial value problem. But this is the basic idea behind an antiderivative, is that it's reversing the concept of antidifferentiation, and the name that we give to that is the integral. So specifically, rather than call it derivative and antiderivative from now on, we're going to call it derivatives and integrals. Integrals are going to undo the process of differentiation, but they can't do it completely. I have to give more information, like I have to tell you what value the function has at a certain point if I want a specific antiderivative. The best I can do is come up with a general antiderivative involving the arbitrary constant c, which we call a constant of integration. So this is the definition of an antiderivative. We're going to do several examples of calculating antiderivatives in class just to get you used to them. But the main idea is, if you know what the formulas are for derivatives, we're basically just going to undo those. And so we'll talk more about that in future videos and in class, but thank you for watching.